Good morning, students. In the previous class, I have explained you all about the standard reduction potential, and in today's class, we will know about other properties, that is general properties of transitional elements, that is formation of complex compounds. Formation of complex compounds. Here in this transitional elements, they form a complex easily. The reason is, three reasons are there, that is due to their size, and second reason is availability of vacant d orbitals and have the high nuclear charge. These are the three reasons why they form the complex compounds. First point is size. Size of metal. Coming for the size of metal, the metal size should be small. They should have a size small. Small size, it facilitates the formation of coordinate compounds or complex compounds. They help in the formation of coordinate compounds or complex compounds when the metal size becomes small. When the size of the metal, that is the central metal size, should be very small, then it favors the formation of coordinate compounds or complex compounds. Second point is they should have high nuclear charge. High nuclear charge or the charge density. Charge density should be high. Why it should be high? Since if it is having a very high nuclear charge, you all know that the central metal atom is always positive in nature. It is a point and it is positive in nature, and the ligands come and attach to the central metal atoms, and those ligands acts like a negative charges. Therefore, they should be having a high density charge. The density of charge should be very high for this formation of complex compounds. Third point is availability of vacant d orbitals. In valence bond theory, that is VBT, you all have studied that there will be a central ligand, with ligands will be, not a central metal atom. For the metal atom, the ligands come and attacks. When you all know the nature of the ligand. The nature of the ligand is that they donate the lone pair of electrons. When these electrons are donated by the ligand, there should be some space for the ligands, that is donated electron, to occupy. In this d block elements or the transitional elements, there is the availability of d orbitals. Therefore, they have the availability of d orbitals, and it helps in the taking of donated electrons from the ligands. These are the three reasons or which helps in the formation of complex compounds. Understood, students? What are the reasons or which are the factors that favor the formation of complex compounds? First factor is the size of the metal. It should be always small in size. This favors the formation of complex compounds. And also the density, the charge density should be very high. If they have a very high density, then it favors the formation of complex compounds. And next is availability of vacant d orbitals. You all know that the transitional metals have a vacant d orbital, so that they can occupy the electrons that are donated by the ligands. Next property, general characteristics. Catalytic nature. Catalyst, they are good catalysts. Catalytic nature of d block elements or transitional elements. This d block elements or transitional elements acts as a good catalyst. We know that nickel, palladium, platinum, chromium, manganese, iron, all these are a good catalyst in d block elements. Here, these acts as a good catalyst. The reason is what? That is availability of, or they have variable oxidation state. availability of variable oxidation state. You all know that the maximum oxidation state for transitional metals is +7 oxidation state. I have explained you all. Therefore, it is having a variable oxidation state and it shows the maximum of +7 oxidation state in it. Since it has a variable oxidation state, it can attach many elements towards itself and it gives out energy and they form as a good catalyst. You all have studied the iron acts as a catalyst in the preparation of ammonia in Haber process and also the platinum in the preparation of sulfuric acid in contact process and preparation of nitric acid in Oswald's process, and also you all have studied about the catalyst in D block elements. The reason why they are good catalysts means due to the availability of variable, they have, sorry, not availability, they have the variable oxidation state. They show variable oxidation state. And in adsorption theory, you all have studied that in adsorption theory, that is, you all have studied the transitional metal ions or transitional elements. They are in, when they are in powdered form. When they are powdered in the powdered form, what happens? The surface area increases. The surface area increases. When the transitional elements are in the powdered form, their surface area increases. When the surface area increases, what happens? These reactants come and occupies this surface area. They takes away the energy and they are converted into reactant and they are removed from it. So, they act as a good catalyst. And also availability of vacant d orbitals. This also favors the formation, that is, due to availability of vacant d orbitals also, they act as a good catalyst. That is, transitional elements act as a good catalyst. Next, coming for the interstitial compounds, formation of interstitial compounds. Formation of interstitial compounds. What are these interstitial compounds? How they are formed? Let us know now. Okay. Interstitial compounds means you all know that any atom, or if I take any metal, this metal is made up of, I am taking an iron rod. Okay. This is made up of what? Small atoms. It is made up of combining of atoms. When these atoms combines together, they form a element or a metal. Here in this, there is an empty space in between this combining of atoms. There is a empty space. You all can see there is an empty space. This empty space is called as holes or sites. These are called as what? Holes or sites. For this empty space, when a non-metal comes and attacks, the non-metals are what? Hydrogen, chlorine, boron, oxygen. These are all non-metals. That is carbon, hydrogen, nitrogen, boron, oxygen. These are nothing but non-metals. When these non-metals come and attach with the metals, that is the empty space, come and occupies the empty space. They are called as interstitial compounds. They are called as what? Interstitial compounds. Interstitial compounds means what? Combining of metal with non-metal. Metal combines with non-metals. is called as interstitial compounds. Here, when this metal combines with the non-metals, what is its nature? What happens to its the property? Coming for the property, they form very hard substance. The obtained interstitial compound will be very hard. They are hard in nature and they are inert. They won't react with any other. They are inert in nature. Okay? They are very hard and inert in nature. These are called as interstitial compounds. It's clear, student, what is interstitial compounds? That is when a metal combines with a non-metals. That is when the metal, in a metal if there is a holes or a sides, for that position if a non-metals come and attacks, they are called as interstitial compounds. The compound that is formed is very hard and it is very inert in nature. It is inert in nature and also it has very high melting and boiling points. Melting and boiling points. They have very high melting and boiling points. This is about the interstitial compounds. Next we will know about the alloy formation. How the alloy is formed. Alloy formation. How the alloys are formed. Here the alloy is formed by the combination what? Combining of metals or metal and a non-metal. It results in the formation what? Alloy formation. Alloy formation is formed by the combining of a metals or metal and a non-metal. When a metal combines with a non-metal or metal combines with a metal, there is a formation of alloy taking place. There is certain condition for the formation of alloy also, that is the atomic radius. Atomic radius should be nearly equal to 50% greater or 50% lesser. I'll take an example here. I am taking a metal here, A. If it is 100 picometer in nature, when this combines with another metal, that is it should be 115 picometer, that is maximum, and otherwise it should be less, that is 85 picometer, it is minimum. Other than this, if the value is other than this, then there is no formation of alloy taking place. For the alloy formation to take place, the atomic radius should be 50% greater or 50% lesser. I have taken here an example. If I take an atom here, if it is having a 100 picometer, then when I am combining with metal B, then it should have maximum 115 picometer, that is plus 15%, and less minus 15%, that is 85 picometer. Other than this, if there is a variation in this value, then there is no taking place of alloy formation. So completely in this unit, you all have studied about the different characteristics of transitional elements. Thank you, students. Next I am going to continue with the next unit, that is F block elements or inner transitional elements. Next unit is inner transitional element, that is chemistry of inner transitional elements. Inner transitional elements. This is the second unit, inner transitional elements. You all know that in a periodic table. In the periodic table, you all can see that there is a S block element, P block, D block and F block elements. You all know that D block elements lies in between S and P block element, therefore they are called as transitional elements. Coming for the inner transitional elements or F block elements. Here the elements which comes after lanthanum, that is lanthanum, atomic number is what? 57. Atomic number is 57. lanthanum, the elements which comes after lanthanum here, which is in the third group, and it is in 6th period. Period number is 6 and it is a 6th group, sorry, 3rd group and 6th period. The elements which comes after lanthanum, that is from cerium to lutetium. 14 elements are present from cerium to lutetium. Those are called as lanthanides. That is from cerium to lutetium. Your atomic number of cerium is what? 58 up to 71. They are called as lanthanides. The elements which comes from lanthanum, after lanthanum, that is cerium to lutetium, they are called as lanthanides. And the elements, these are also called as lanthanoids. And from thorium, the element which comes after actinium, here atomic number 89, actinium, that is which is in 7th period and 3rd group. Actinium with atomic number 89. The elements after actinium, that is from thorium, that is 92 lawrencium, atomic number is 103. They are called as actinoids. Here in the periodic table, you all know that the periodic table has been divided into 4 groups, that is S block, P block, D block and F block elements. The elements which comes after lanthanum are called as lanthanoids, and the elements which comes after actinium are called as actinoids. Here in the periodic table, what is the general electronic configuration for F block elements or inner transitional elements? The general electronic configuration. Here NS2, N minus 1 into D, 0 to 1, N minus 2 into F, 0 to 14. This is the general electronic configuration for F block elements, that is inner transitional elements. What is inner transitional elements? Inner transitional elements means what? The differentiating electrons enters into N minus 2 into F subshell. Differentiating electron enters into N minus 2 into F subshell. These are called as what? Inner transitional elements. Inner transitional elements. Here, this is the valence shell, NS2 is the valence shell, and this is the ultimate shell, and this is the penultimate shell. Okay? This is the valence shell, ultimate shell, valence or ultimate shell. This is penultimate shell. This is anti-penultimate shell in the F block elements. This is the general electronic configuration for F block elements. And the elements which comes from after lanthanum, that is from cerium to lutetium, they are called as lanthanoids. Why they are called as lanthanoids? Because they show the similar properties of lanthanum. Therefore, they are called as lanthanoids. And elements from thorium to lawrencium are called as actinoids. Why they are called as actinoids? Because they show the similar properties of actinium. Therefore, they are called as actinoids. Next, you all came to know why they are called as actinoids and why they are called as lanthanoids and actinoids. Here, this lanthanum, it is in N is equal to 2, sorry, N is equal to 6, 6th period. It is in 6th period and it is in 3rd B group. It is in 3rd B group. Here actinium, it is in 7th period. Period is 7th period and it is in 3rd B group. Actinium is in 3rd B group. Both are in 3rd B group, but the period for lanthanum is 6th period and for actinium it is in 7th period. You all can see here in the periodic table, here N is equal to 6, that is lanthanum, and N is equal to 7, that is actinium. Here it is in 3rd group, that is 3B group. Coming for the electronic configuration for lanthanum. You all know that the general electronic configuration of this F block element is this. When N is equal to 6, you will get the general electronic configuration for lanthanoids, that is lanthanoids. And if N is equal to 7, you will get the electronic configuration for actinoids. Here, if I substitute the N value here 6, then 6s2, 6 minus 1 is 5d, and N is 6, 6 minus 2 is 4, 4f, 0 to 14. Here 0 to 1, 5d 0 to 1, 6s2, 5d 0 to 1, 4f 0 to 14. For actinoids, if I substitute 7 here, it is 7s2. 7 minus 1 is 6d 0 to 1 and 5f 0 to 14. This is the general electronic configuration for actinoids and for lanthanoids this. So now let us go for the electronic configuration, how to represent the general electronic configuration for lanthanoids. You all know that the elements, these lanthanoids are nothing but they are 4F, that is 4F series. These are 4F series elements are called as lanthanoids, and 5F series elements are called as actinoids in the periodic table. Coming for the electronic configuration, I am taking the elements that is from cerium to lutetium, all the 14 elements, how to represent the general electronic configuration for 14 elements. First is lanthanum, then comes cerium, then comes praseodymium, then comes neodymium, then comes here promethium, PM, then samarium, europium, gadolinium, then comes terbium, then dysprosium, and next holmium, europium, then thulium, ytterbium, and lutetium. These are the 14 elements that are present in lanthanoid series. This atomic number of lanthanum is 58, then 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 58, 59, 60, 61, 62, 64, 65, 66, 67, 68, 69, this is 57, lanthanum, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71. This is the atomic number of different elements in the inner transitional elements. Coming for the general electronic configuration, you all know that the lanthanum, it has the general electronic configuration of, that is, what is the atomic number? It is having 57. Before this, the noble gas, that is xenon, it is having an atomic number of 54. I can represent xenon, that is atomic number is 54. Remaining is 3 electrons, that is 4f, 5d 6s. I will represent this for all the elements like this before writing remaining electrons, that is xenon 4f 5d 6s. Then for this xenon 4f 5d 6s, xenon 4f 5d 6s. For all the elements, I am just writing this electronic configuration first up to xenon and 4f 5d and 6s, and then I will start filling the electrons in it. In this transitional elements, that is inner transitional elements, the filling of electrons does not take place according to Hofbauer's principle. Most of the elements in the periodic table obey the Hofbauer's principle, but certain elements are there which does not obey the Hofbauer's principle. Like that, in the inner transitional elements also, there are certain elements which does not obey the Hofbauer's principle. 5d 6s, in this lanthanum, you all know that the atomic number of xenon is 54, remaining is 3 electrons. The filling, you all know that 2 electrons are completely filled in this valence shell. Before that, you can fill the 2 electrons here in the valence shell. It's almost filled, the valence shell is completely filled. That is, S subshell is completely filled in all the elements. Coming for this, remaining 1 electron, it is taken in D subshell, F becomes 0. This is the general electronic configuration for lanthanum. Coming for cerium, here for the representing of this general electronic configuration, actually it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But it's not like that. There is a change in the representing the electronic electrons in the F subshell. What happens in cerium? D subshell is empty, it becomes 0. 2 electrons are occupied here, that is nothing but 58. 54 plus 4 electrons is 58. Next is, in this 3 electrons, 5d is 0. Total is 59. Here in this 4 electrons, 6, 0, this is 5d is 0 and 6s is 2 electrons. Next, promethium, in that 5, this is 0, 2 electrons. Then samarium, 6, 0, 2. Total is 62. 54 plus 6 is 60 plus 2 is 62. Next, here it becomes 7 and 1 electron, here 0. 7, 2 is 9, 9 plus 54 is 63. Next is xenon, that is 4f7, 5d1. Here gadolinium, what it does means, it doesn't give 1 electron is taken by D subshell, because this F subshell becomes stable here. That is, you all know that F subshell becomes stable when it is having unfilled or half filled or completely filled. Then only it is stable. We say that F subshell is stable when it is unfilled, half filled and completely filled. This gadolinium, it will be in half filled state, therefore 1 electron moves to 5d subshell. Next is terbium, that is here 64, 54 plus 9, 54 plus 9, 9, 10. Total is 64. Next is terbium, 6s2, 4f, 9, then 55. Then here it is 10, it is 0, here it is 11, 12, 13, 14 and 14. Here what it becomes 0, 0, 0 and 0. Sorry, here it will be 0 and here it is 1. It will be having 1. That is 14 plus 1 is 15, 16, 17, 17 plus 54 is 54 plus 17 is 71. Okay. Therefore, lutetium is having completely filled, that is 4f14, 5d1, 6s2. This is the general electronic configuration of this inner transitional elements. Here, which does not obey the Hofbau's principle is cerium. You all can see here, cerium is not obeying the Hofbau's principle. Yes or no? And gadolinium, europium, gadolinium and ytterbium. What happens? These are not obeying the Hofbau's principle. Here, in this general electronic configuration, you all came to know how to represent the general electronic configuration of this inner transitional elements. In cerium, in F subshell 2, you all should observe here, students, here F becomes 0, after that 2, 3, 4, 5, 6, 7, 8 is not repeated, again 7 is repeated, 7, 2 and 8 is neglected in representing the F subshell. Okay. Easiest way is F subshell. In F subshell, how many electrons it can occupy? 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, I will represent it here. In F subshell, how many electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Maximum 14 means 14 electrons it can occupy. To fill this F subshell, you should neglect this second and 8th electron. Here for F, 1, for this second position 3, for third position 4, for fourth position 5, 6, 7, for 7, it is 7, for this 8, for this 9, for this 10, 11, 12, 13, 14 and 14. You all can see here. What happens? Here F2 is neglected, F3, F4, F5, F6, F7, again F7, F9, 10, 11, 12, 13, 14 and 14. Second and 8th electron should be neglected. So now, next is, you will know about the oxidation state. What is the oxidation state in inner transitional elements? Inner transitional elements, these maximum oxidation state of inner transitional elements is +4. +4 is the maximum oxidation state of inner transitional elements. And common oxidation state of inner transitional element is +3. Here this inner transitional element shows the common oxidation state of +3. +3 is the common oxidation state. Why this inner transitional element shows the +3 oxidation state? In this inner transitional element, first point, the IP1, IP2 and IP3, they are nearly they are low. That is, if I take a lanthanum, that is, if I remove one electron is removed, it becomes Ln plus. If second electron is removed, that is IP2, one more electron is removed from it, then it becomes Ln2 plus. If one more electron is removed, that is IP3, then it becomes Ln3 plus. Here they have low IP1, IP2 and IP3, and there they show negative standard reduction potential. They have high negative standard reduction potential. They have the high negative standard reduction potential in +3 state. Why? If I take lanthanum, when it undergoes oxidation, it loses 3 electrons. So, standard oxidation potential will be positive. It has value, positive value. When this lanthanum 3 plus undergoes reduction, it forms lanthanum, standard reduction potential value will be negative. They have very high negative standard reduction potential also. They have high negative standard reduction potential in +3 state, and they have, that is, they are having a hydration energy is very more. Hydration energy is very more. Even the hydration energy is very high. These are the reason why they show the common oxidation state, that is +3 is the common oxidation state in this transitional elements. Here, as I said, all the elements shows the +3 oxidation state, but this cerium, lanthanum and cerium, if I take lanthanum and cerium, here it is stable in +3, this is also stable in +3 plus +4, both the state cerium is stable. Here this cerium, when it is in +3 state, its electronic configuration is 4f1. It has one valence electron in it. But when it goes to +4 state, it loses one more electron and it becomes more stable. Therefore, Ce4 plus is more stable than Ce3 plus. Here it is having one valence electron, it is more stable because it is unfilled. You all know that unfilled is stable. Unfilled, half filled and fully filled electronic configurations are more stable. Then if I come for europium, even in this, that is europium 2 plus is more stable than europium 3 plus. Why? Here in this, the electronic configuration, it has 7 electrons. When it removes one more electrons, here in this europium, it has 7 electrons, that is xenon 4f7 6s2, in gadolinium 4f7 5d1, and in europium and terbium, ytterbium, that is, you all should see which state is more stable. Okay, here in 3 plus, it will be having 7 electrons. In the 3 plus 4f6, here in 2 plus it becomes 4f7. This is half filled. Even in half filled state it is stable. You all know that completely filled, half filled and empty, they are more stable. Coming for the ytterbium, even this ytterbium 2 plus is more stable than ytterbium 3 plus. Here it is having 4f 13 electrons, it becomes 4f14 when it is in ytterbium 2 plus state. Therefore, it is more stable in the +2 state. Ytterbium is more stable in +2 state. And also you all know that maximum oxidation state of transitional element is +4 and minimum or common oxidation state is +3. And it also shows +2 and +4 oxidation state, including +3 oxidation state. +2, +3 and +4. All these are shown in inner transitional elements. All these oxidation states are shown in inner transitional elements, but most stable oxidation state is +3 oxidation state. Coming for the color of the transitional elements. You all know that cerium, the elements are cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, then comes terbium, dysprosium, central per nazar do PM, some shame on you, good things are dying. Good things are dying. Hope in this year time. Hope in this year time you will look. This is the easiest way to remember these elements. How? Central per nazar do PM. Cerium, promethium, neodymium, promethium, praseodymium, this is praseodymium, this is promethium. Shame on you, samarium, europium. Good things are dying, gadolinium, terbium, dysprosium. Hope this year time, that is holmium, europium, thulium, and you will look, that is ytterbium and lutetium. The first, after lanthanum, first comes lanthanum, that is 57 to 71. Even though these two are colorless, they are colorless, and this gadolinium is colorless, but last two also is colorless. Why these are colorless in nature? Because they are not present in visible region. These elements does not comes to visible region. They are obtained in UV region. Therefore, they are colorless in nature. But other elements, even in +3 state, they show color. Why they impart color? Because they come under this visible region, that is between 490 nanometer to 780 nanometer. Visible region, you all know the visible region, that is between 490 to 780 nanometer. You all know that any elements observes its color and gives a complementary colors, observing one color and giving the complementary colors. Like that, in the transitional elements also, they observe one color and give the complementary colors. Here praseodymium gives pink color, bright pink. The color is bright pink, and it has n is equal to 1, n is equal to 2, valence electrons 3, 4, 5, 6 and n is equal to 7. Here what happens, I am taking from here, that is 14 minus n. 14 minus n, 14 minus n is what? For this terbium, it is having the electronic configuration of 65. It has the electronic configuration of 65, that is xenon. It is 54. Then 4f, 6s2, 5d, 4f. it is 2, 54, 55, 56, 56 plus 56 plus 9. 9 electrons are there. 14 minus 9 is what? You will get 6. That is this. Here, this, it is having the atomic number as 69, that is xenon. 5d 0, 6s2, that is 56 plus 14. 56, 69 minus 56 is what? Here you will get 3, then 1. 13 electrons are there in 4f subshell. 13 minus n, sorry 14 minus 13, it is having 1 electron in its outermost shell. Like this you are going to calculate. If it is having a bright pink here, even this has a bright pink. It has a bright pink. It is having a pale or pink color in nature. They have a pink color. Here if it shows, sorry, it shows green color here. It is green in nature. This is pale green. Then bright pink. This shows pale pink. This is having pink yellow color. It shows pink yellow. This is yellow. This is having a yellow color, and that also has a yellow color. Like this, the colors, that is n is equal to 2 means, if its n value is equal to 2 means, same color is obtained by both of them in the +3 oxidation state. Other than this, these cerium, if I take a cerium and ytterbium, in cerium +3 state and ytterbium +3 state, these two don't show, they are colorless in nature. Why they are colorless in nature? But other shows the colors when there is a unpaired electrons. They are having a more number, means if they are having an unpaired electrons means they impart the color. But the cerium and ytterbium, they won't impart the color, they shows the colorless even though there is a valence electrons in it. That is, it has 1 valence electrons, and in this also there is having a 6 valence electrons in it. Even though it has a valence electron, it is colorless in nature because they are not observed in the visible region. They won't fall in the visible region, they fall in the UV region. Therefore, they won't shows the colors. Due to FF transition in the band, what happens? They observe the colors and they emit it complementary colors. That is, in transitional elements, their band is very thin in nature. It is very thin, but it is very sharp compared to transitional elements. In transitional elements, their band is very thin, but they are very sharp and compared to transitional elements. So, in the next class, we will study about the different properties of inner transitional elements. Thank you, students.